Hey guys, welcome back to my YouTube channel. You are watching Build AI with Sandeep. In my last video, we saw that when researchers tried to make deep transformer models, then there was a problem of vanishing and exploding gradient problem. And we know that the three fixes made by three different teams. The first one is optimizer fix that was done by University of Tokyo. The second fix is activation function fix in the activation function that was done by Google Brain. And there was a third fix that was done by LLM community in the transformer architecture. So I plan to make this video in two parts. In first part, we understand what is transform, what is optimizer, and what are its different types, important types. And in the second video, we will understand what fix made by the university team in University of Tokyo. So let's quickly start our today's video. What is optimizers? So let me take you to. So let's simply understand first what is optimizers. So it is a method that updates model weight to reduce loss. Method that update weights to reduce loss. That's it. That is the optimizers. So let's understand more simply that in a neural network, like this is the neural network. This is the simple neural network. These are x1, x2 simple. These are our input, and we multiply it weights, add a bias, apply activation function. Then we get our y cap. So in neural network, mainly three steps. Neural networks training include three steps. The first step is forward pass. Forward pass that gives us this y cap prediction. And the second step is compute loss. Compute loss. That is y cap minus y whole square. This is our loss calculation. Then thirdly, what we do is we do back propagation. I want to correct here that in back propagation, weights does not change itself. In back propagation, we only get the gradients, derivatives. We only get the gradients. Derivative of loss, derivative of weight. This is the gradient. And these gradient tell us the direction. Now, let's understand the terminology that why we are using optimizers to update weights. What is the necessity? So, firstly, in neural network, they does not change weight itself. Okay, and let's understand that we compute loss. I'm saying that loss is this. This is our loss, and this y cap is dependent on weights. Dependent on weights. You know the y cap weight equation w1 x1 plus w2 x2 plus bias. So this y cap is depend on weights w1 and w2. So if we only have this w1 x1, okay, then we can plot the curve of loss and this w. So when we put this equation w1 x1 plus b minus y, okay, so now we can draw a graph in two-dimensional space. So y cap shows loss and this is w. So when we make any change in weight, then how much loss will increase or decrease? What will be the change in loss? Okay, so so there are multiple weights. There are thousands or millions of weights present in in deeper models, in deeper deep learning models or transformer models. So in that case, this graph is in 2D plane, but there are multiple planes. High dimension, very high dimensional, and we cannot visualize that. So our goal is to change in weight in such a way that the loss will be minimum. Change in weight so that our loss will be minimum. So let's suppose it is like when in high dimensional plane, let's suppose that let's imagine that our loss curve is like mountain. So this is like mountain. Okay, this is our loss curve, and we are imagining that it is a mountain, and we are standing right here. Okay, and our main goal to use optimizers is to reach at this point, and this point is global minima. Global minimum. Okay, so when we are at this point, what we need two main things. The first thing, we need direction. That okay, we are on the top of mountain, and we need to move in this direction. The first thing we need. The second thing, we need step size. Sometimes the mountain in real world the mountain is like this. So sometimes the surface is flat, then we need to take smaller step, and sometimes it is steep like this here, then in this case we need to take larger steps. So so we use this rule. So we use this equation, optimizer equation. And what is that optimizer equation? I told you in my previous videos multiple times. Old minus learning rate times derivative of loss divided by W old. So in every type of optimizer, we use the same equation. Here, the direction, this gradient tells us the direction, and this learning rate tells us the step size. See, without learning rate, we cannot able to reach at this global minima, because sometimes this gradient is very large, then our training explodes, and sometimes it is very smaller that the W old will not change in that case. So we need learning rate. It works as a scaling factor. Okay. Now let's move ahead. Now let's understand its types. Optimizer type. What are the famous optimizers? We are going to discuss firstly gradient descent, the first. Then there is stochastic gradient descent. Stochastic gradient descent. Thirdly, there is momentum. So this video is like recap of deep learning optimizers, and it is really good. It will help us to understand the first fix. The fourth one is RMSprop, and the fifth is Adam optimizer. And the Adam optimizer was used in transformer architecture. So we need to understand Adam first, and let's see. So let's take one by one. So gradient descent. So every optimizer uses the same equation. There will be small tweaks, but the core of the equation will be the same. And the whole the main aim of optimizer is to update weight in such a way that our loss will be minimum. Okay, and so let's understand gradient descent. So gradient descent, what it does is it uses entire dataset to compute gradients and model weight. So let's suppose that we are working on a regression problem and we are predicting prices based on the car features. So let's suppose we have car features like X1 that represent make, X2 model. So multiple features, we have 10 features and we need to predict price. So P1. So that is our price. So we have 100 rows data. So in training, we need to perform like we are training our model. So we pass one row, first row, and we predict price 1, P1 cap. We pass second row, P2 cap. We are not updating weights. First, we are giving all the rows to our model and we reach to the 100th row. And then it predict P100, price 100. Then we compute loss. So in gradient descent, we use all the data set, we predict all 100 prices, and then we compute loss. And the loss will be 1 by n summation of p cap minus p I 1 to 100. Okay, so in this way, we compute loss and then we update weights using the same formula 1 to 100 and pi cap minus p. So we use the same formula and then we update weight and then we again then in the see the whole process is said to be epoch. We say epoch that okay in first epoch all the 100 row processed and we take 100 prices, our 100 predictions, then we compute loss, average loss, and then we update weight, and in the second epoch we do the same until we reach the global minima. See in first epoch maybe our loss will be right here. Okay, then we move in second epoch, we move right here in third epoch, in fourth epoch. So in all epochs we use the entire data set and then we update weight. Okay, so this is the gradient descent. Now let's move to the stochastic gradient descent. So stochastic gradient descent update weights using one data point at a time using the same formula. Stochastic gradient also use this same formula, but this time we are unlikely gradient descent that uses whole data set, but this time we predict one price and then update weights. Update weight. Yeah, in first iteration, we predict price and we update our weight. Then in second iteration, our weights, our prediction will slightly better than gradient descent because we update weights. The second, again, we update weights. Then again, like 100 times we update our weights in one epoch. In one epoch, we already updates our weight 100 times. So there is probability that SGD works better than the gradient descent because gradient descent was taking too much time because it uses full data set to update weight. But in stochastic gradient descent, in one epoch, we already updated our weights 100 times. So this is better, but there are some pros and cons. So let's understand the pros of gradient descent and SGD. Both uses the same formula. Nothing changed in the core formula of optimizer. So gradient descent, the pros are It is stable. It is stable and convergence, smooth convergence. And pros of SGD, it is fast. Why fast? Because every time we update weight, and then in the second pass, our prediction will be better, loss will be less because we update weights. So in this way, SGD is fast. Work for larger data set. Work for larger data set. See, if our data will be large, then gradient descent will take too much time to reach convergence, to reach local minima. Now there are some cones. So these are our pros and these are cones. And the cons of gradient descent is very clear that too much time to reach global minima. And the cons of SGD is that noisy updates, zigzag movement, zigzag movement. Let's understand this thing that why noisy, that SGD is better than gradient descent, but why noisy updates? See, every time when it predicts prices and update weights, so how it is updating weights? Calculating derivatives. Okay, it is calculating derivatives, and this gradient is telling us the direction. I told you direction. Gradient gives us direction. So due to this direction, the movement is like this is global minima. So our SGD will SGD travels like this, like this, because every time it is computing gradient, there is new direction information. So due to the new direction information, the updates are noisy and zigzag movement. This is the problem with stochastic gradient problem. So nowadays we use mini batch gradient descent. In this case, we use batches. Like we have 100 rows, so we take 10 rows batch. So our batch size 10 rows. Batch size 10 rows. So this is this is better comparatively to SGD. Now we process 10 rows. We first get 10 predictions and according to our batch size, and then we compute loss. We get prediction. Just a second. So in this case, we predict 10 prices, compute loss, compute gradients, then update weights. So using this batch gradient descent, mini batch gradient descent, and batch size can be anything, can be any number. We can make a batch of two for 100 rows, like 50 rows first, 50 rows second. So in one epoch, we did the two weight updates. Okay, so this is slightly better. We were able to reduce some noise in our training, and the zigzag movement also reduced. But now the third optimizer came, momentum. Momentum. In momentum, we first understand the problems with SGD. Problems with SGD. So there are two problems. First is oscillates too much, oscillates, and the second is slow in narrow value. So these are two problems. So sometimes, because due to the computation of gradient in every iteration in SGD, there is new direction, and that is why our training, our updates oscillate. There was some noise in our learning. So momentum says that why don't we remember the past five gradient direction? If the past five gradients or past five or any number past gradients, we can say that using the direction of past gradients, why can't we follow the same direction? We can remove the noisy updates, we can remove the zigzag motion. Okay, so momentum add the memory of past gradients. So idea was simple. Momentum adds the memory of past gradients. So let's understand the formula of momentum. So momentum adds this velocity factor. Beta is hyperparameter here. This is our gradient. This is same like this. Okay, we can also write the same derivative like this notation. Okay, and now here the optimizer formula will be learning rate times v. So nothing new in momentum. Momentum uses again the same core equation of optimizer, but there is a velocity parameters, and momentum says that we are following the same direction of past gradients to increase the speed of our learning so that we can reach global minima fastly. That's it. So it keeps the part of previous direction, reduce oscillations, move faster in consistent direction. Let's understand this using example. If gradients are repeatedly positive, velocity increase, steps becomes bigger. So you can understand this statement that if gradients are repeatedly positive, velocity increases and steps becomes bigger. So it take momentum helps to take bigger steps. Now let's understand the RMS Pro. RMS Pro. So RMSprop says that now we changed now in the optimizer equation we add the velocity part, and we made a change in our derivative somehow. Previously we were using the same derivatives here, but we add the velocity part. Now it is time to make some changes in the learning rate. RMSprop says that same learning rate for all direction is bad. Some directions are steep where we need to take larger steps, and some directions are flat where we need to take smaller steps. So the idea of RMSprop is reduce step is gradient is large and increase step if gradient is small. So if we can see in our in this case, so in this diagram, let just see in this diagram, there are multiple local minimas in real life. In real life, in mountains, there are multiple local minima. So our gradient will stuck in these local minima sometimes. So we need larger steps so that our gradient will not stuck in these local minima and come out from these and reach the travel to the global minima. So for that purpose, momentum helps and also RMSprop also helps. So let's understand again. So RMSprop at a step equation, step size. So RMSprop uses this formula. Also, I forgot to tell you that this beta value is mostly zero point 0.9 in momentum. And now in RMSprop, the step size equation is beta s plus 1 minus beta, and derivative of, okay, this is our gradient. So this takes square of gradients. This is the equation of step size, and W then minus learning rate times S plus epsilon. So this is the equation used by RMSprop to update the weights. And here the new thing is this step parameter. Using this, we are taking different learning rates for different gradients. Again, if the gradient is large, if the gradient is large, then S large, step small. See, if the denominator, this is in our denominator, if S is large and this is denominator, then our step will be small. Okay. And if gradient is small, the opposite happens. Gradient is small, S small, and then step larger. Effect. What are the effects of this RMSprop? The effects are, we say it, adaptive learning rate. That our learning rate adapt during the training. Learning rate. And the second is more stable than SGD. So in a way, we can see that the momentum and RMSprop both are solving the problems of SGD, stochastic gradient problem. For noisy updates, again, RMSprop help to make the stable gradients, stable updates, and for speed, controlling the speed. SGD was like too fast because every time it is updating weights and it forgets the direction. So momentum controls the speed of SGD, and RMSprop gives more stability to update the gradients. Now finally, we are here to understand the Adam optimizer. So uh, be careful at this step because this is very important optimizer, and this is nothing but this is very simple. If you understood the momentum and RMS prop, then it is very easy for you guys to understand this Adam optimizer. So Adam came and said that I like the idea of momentum as well as I like the idea of RMSprop. So Adam is nothing but Adam is momentum plus RMSprop. Okay, so it keeps both. It keeps mean of gradients, mean of gradients direction. This is momentum part, and mean of square gradients. This is step size control. So now let's look at this. Look at the formula. Look at the equation. So firstly, there is a momentum part. M equal beta 1 m plus 1 minus beta 1 gradient. The second is step size. Beta 2 v plus 1 minus beta 2 gradient square. Now there is one more step added, bias correction. You cannot find this bias correction explanation easily, but I will explain you this bias correction, and that is most important part, most important step. You will see in my next video when we understand the first fix. So there is a bias correction, M cap. We use the same M that we find here, M divided by 1 minus beta 1 t, and there is a V cap, V divided by 1 minus beta 2 t. Okay, now our final optimization equation. Final equation will be W nu is equal to W minus learning rate times M cap divided by V cap plus epsilon. So M is direction memory, V is step size control. So Adam is finally like fast due to momentum and stable due to RMS. So let's understand what is bias correction. So bias correction is used in Adam optimizer. Adam keeps moving average, the first movement mean of gradients in MT, and the second movement is mean of squared gradients. And the beta 1 and beta 2 value, beta 1 approximately equal to zero point 0.9. Similarly, the beta 2 in second moment is also approximately 0.999. And so what is the problem? Why we need to take bias correction? So let's understand this very simply. So at the beginning M0 is 0. So first update, let's understand the first update. The what is the formula of first movement? Beta 1 m plus, so this will be 0. So let's understand this equation again. Beta 1 m plus 1 minus beta 1 gradient. So in this case, when at the beginning m0 will be 0 plus 1 minus beta 1 gradient, and I said beta 1 is mostly zero point 0.9. So 1 minus zero point 0.9 gradient, and this will be zero point 0.1 gradient. But so in the very first pass, in the very first weight update, true gradient is G. This G is true gradient, but our equation, first moment equation, if we don't use this bias correction, then this m will be zero point 0.1 g. It means 10% of the true gradient, 10% of the real estimates. So that means moving average is biased toward zero in early steps. Moving average is biased toward zero in early steps. Same happens for the VT, the second moment. This is called initialization bias. This is called initialization bias, and model takes many steps to gain speed. That's why we are using this bias correction. So this bias correction fixes the underestimation. This removes the zero initialization bias, and why, and you must be thinking that why we are dividing by 1 minus bt. So let's understand this. Let's understand the y part of 1 minus bt. Understand the intuition. So the empty is like 1 minus bt gt plus beta 1 gt minus 1 plus beta 1 square gt minus 2 plus if gradients is constant g, then mt is equal to 1 minus beta t g 1 plus beta 1 plus beta 1 square plus beta 1 t minus 1. So this is the geometric series. If you remember the mathematical equation of this geometric series, 1 minus beta t divided by 1 minus beta. So mt is equal to, so mt is equal to now g1 minus beta 1 t. So to get true g, to get true g, m cap is equal to mt divided by 1 minus beta 1 t, and we know mt is equal to 1 minus beta 1 t, 1 minus beta 1 t. This could cancel out, and this is g. So bias removed. That is why we are using this bias correction, and it removes the underestimation bias. Underestimation, it fixes the underestimation at the beginning. So that is why we are using bias, and you can also you can also see using this simple example. Example, numerical example. Assume beta 1 equal zero point 0.9, gradient equal 10. Okay, so the m1 is equal to 0.1 into 10. At the very first, if I have to, just a second. So m1 is equal to m0 beta 1 plus 1 minus beta 1 gradient. Okay, so m0 is 0 plus 1 minus 0.9 is 0.1, and the gradient is equal to 10. So we get 1, very small. So now bias correction m1 cap equal 1 upon m1 is 1, 1 minus beta 1, so 1 upon 1 minus zero point 0.9, so is equal to 10 again. Now you can see that using this bias correction, at the start we get the value of m1 cap is equal to the true gradient. Okay, so in step 2 you can see the magic. In second update, m2 is equal to zero point 0.9 multiplied by 1 plus zero point 0.1 multiplied by 10 is equal to 1.9. So in second update, the m1 value is zero point 0.9, and no, this is beta value is zero point 0.9, and the m0 value is 1. We computed m0 value is 1. Okay, m1 value, this is m2. So beta 1 m1 plus 1 minus beta 1 and g. Okay, so using this equation we get m2 value is 1.9. Without correction 1.9 still small. Now m2 cap will be 1.9, 1 minus zero point 0.9 square, it will be 1.9, 1 minus 0.81 is equal to 10. Correct again. So again it is correct. So what happens if we don't use bias correction? Early training, M is too small, V is too small, update becomes very small, and training becomes slow at beginning. Model takes many steps to gain speed. So that is why we use bias correction, make early training accurate and stable. That is it. Bias correction removes the zero initialization bias in Adams moving average so that early updates are accurate. So, yes, guys, that is all about the optimizers. I hope you understand the whole concept of the optimizers. So in summary, I want to tell you that optimizer are used to update weights because there is no mechanism in neural networks itself to update weights. So by optimizer fills the gap, and optimizer uses the simple equation W nu is equal to W old minus learning rate times the gradient. And in this formula, learning rate decides the step size, and the gradient tells us the direction in which direction we need to move. And there are mainly five important optimizers. The first one is gradient descent, that take all data set to update weight in one epoch. But in stochastic gradient descent, we make a prediction and we compute loss and then we update weight. Then we iterate this multiple times, that respective to our number of rows in our data set. Okay, then came momentum, that increase the speed of that control the speeds of the stochastic gradient descent and removes the noisy updates. And then RMSprop came with the idea that same learning rate with the all the directions with every step is not so good. We need to control the step size. Sometimes we need larger steps, sometimes we need smaller steps. So that is why RMSprop came. And then finally Adam came, and it tells us that the momentum and RMSprop are both very good. So why don't we combine the idea of both? So Adam gives us the better. Adam was the very popular optimizers at that time, and in transformers the same Adam optimizer used as uh, as the optimization as the updating weights inside the transformer architecture. And now I want to say that in our next video we will see that there is a flow in Adam optimizer also, and that cause the vanishing and exploding gradient problem in the training of large language models when researchers tried to make deeper models. So, so that is it for today, and thank you all for watching. If you like the video, if you learn something new today, then please do like, share, and subscribe my video. I will see you in my next video. Thank you so much.